Neurosom has pioneered the use of several AI technologies in its research and product development. Given the intense public interest in how advances in AI could further medical device capability, Neurosom is providing a series of webinars for our scientists and engineers to explain the role of AI in our products and clinical trials, as well as to address questions about patient safety and medical device regulation.
The EEG reflects neuronal activity of the cortex during wakefulness and sleep. It's characterized by voltage changes over time, and it appears as waveforms when recorded. There are patterns embedded within these waveforms that are meaningful about normal and abnormal brain functions. These patterns in the EEG also allow us to determine the transition from wake to sleep and what stage of sleep a person is in for any given time. And over the course of the night, the changes allow us to characterize the complete cycles of sleep for a given person. And the EEG is the gold standard for sleep staging. However, the problem is that identification of the relevant EEG patterns traditionally has required extensive human training and time to read and review the EEG records. This is particularly problematic for applications in which the goal is to identify a certain brain state and modulate the brain activity given that state. With the ability to automatically and reliably identify sleep stages through the use of machine learning, we can now identify when someone is in the sleep stage that precedes deep sleep. And we can then nudge the person into deep sleep and keep them there for a longer period of time through stimulating the brain structures involved in deep sleep. The same machine learning ability to classify sleep stages also allow us to efficiently and reliably summarize the person's sleep architecture and duration after therapy. This allows for timely and inexpensive summaries of the sleep of individuals undergoing sleep therapy, enabling clinicians to efficiently evaluate the outcomes.
So we've asked our scientific consultant, Dr. Zenios Papadimitris of Yale University's Machine Learning in Medicine program, a very interesting new program. We've asked him to comment really on this process of using machine learning in medicine. We know there's a lot of concern and failures with this. Dr. Papadimitris, could you comment specifically on Neurosom's machine learning for sleep staging and the challenges for the validation?
So, as I'm sure you're aware, if what we're doing qualifies as a medical device, the FDA regulates it. And just like every other medical device, these things must be validated, verified, all the good words. And the FDA has issued a number of guidance documents. Here is one. The latest is the Good Machine Learning document. It sets up guiding principles, and it's a collaboration between the FDA, Health Canada, and the MHRA from the UK, the English-speaking regulatory agencies, which come together to begin the process here. So this shows 10 good principles. Here they are zoomed in. So this verifies some of what you've heard from Dr. Liu, that training data are independent of the tests, and this is what we're doing. Clear essential information, clinical study participants are representative of the population, multidisciplinary expertise, good machine software engineering, all of the things we have done, plus a few extra that are new for the world of AI. When it comes to AI machine learning, we can distinguish about 3 different types. Let's call them the old style statistical learning methods, beginning even with linear regression, which is now classified as machine learning. Modern deep learning methods beginning the 2010s, 2015, 2016 for medical devices. These are most commonly used for image and signal processing. This is the category we are in. The Neurosom category will be here. And then we have newer techniques based on generative AI methods or foundation models that are particularly valuable for text processing. For example, you've heard about ChatGPT, I'm sure. Now, we don't know how these are going to be regulated. Nobody really does, but we're not in this category here. The FDA helpfully has a table that, if you can go on their webpage, lists all the things that they've cleared With AI/ML, there are now 692 as of 10 minutes ago when I downloaded the table. The oldest one goes into the 95. There are two from the 90s, and I'm sure they're very simple linear regression. The majority of what has been cleared, the great majority, probably 3/4, are in imaging radiology, again, using convolutional neural networks, the technique we're proposing to use. Ours is an 1D imaging mechanism in many ways. The majority, this is over 90%, uses a 510K mechanism, not the 501, 510K mechanism that involves showing equivalence to a predicate. Again, this is a strategy that Dr. Liu outlined for us. So in many ways, what is being proposed here is well established at the FDA level with hundreds of devices approved cleared using this mechanism, using these types of techniques. So we don't anticipate any unique challenges here. Okay.
Excellent. But if we do introduce more generative AI technologies, we don't have good guidelines for how to validate these. Can't we just use the same validation criteria where we show equivalence to a device or we show we can meet criteria with the more novel generative AI?
I expect that is exactly how these things are going to evolve. There will be some challenges in terms of risk management because these things need to be more carefully locked down and restricted to access particular information. So the challenges with all of AI techniques compared to traditional medical devices are basically because these are different techniques, they have different types of risks. And so long as the risk can be bounded and packaged, so with convolutional neural networks, a detailed analysis usually suffices. With the generative AI methods, having some way to restrict the input information into the model to trusted data will probably be the most important component of that strategy.
Great. That's very helpful because in our future webinars, this is in fact what we're going to try to conduct research and development on. So one of the challenges we have then is how can we do this efficiently at the bedside? Let's assume that the real-time machine learning is working and we understand its operation. How can we implement it? So Dr. Roma Schusterman, our Chief Technology Officer, is going to give us a brief overview of the specific implementation of machine learning within the Neurosom sleep therapy package.
Thank you. So let's start from the implementation of the CNN and what is the CNN? CNN stands for convolutional neural network. Convolutional neural networks are a class of deep learning algorithms that have revolutionized the field of computer vision and found applications in various domains. The original idea was inspired by the brain's visual cortex. In the visual cortex, neurons in the different areas process different features of images, starting from dots, lines, and progressing to more complex representations of images. Similarly, different convolutional layers in the CNNs process various hierarchical representations of images. In computer vision, CNNs perform image classification, object detections, and segmentation. There are multiple layers, and different layers perform different operations. There are layers that perform filters feature extractions by filtering. There are layers that perform downsampling, and finally layers that performs decision making based on these extracted features. And CNNs can be adapted to the time series data by treating temporal sequence as a spatial dimension in images. So instead of pixels, time series data points become the input, and convolutional filters slide along the time dimensions to extract temporal features. So we implemented the convolutional neural network for sleep staging on NVIDIA Jetson Nano, small, powerful computer designed specifically for artificial intelligence and deep learning applications at the edge. It's equipped with the GPU capabilities of running complex neural networks models efficiently, making it ideal for real-time inference tasks like object detections, image classifications, or time series processing. So
That's great. Thanks very much, Roma. So one of the challenges we have, once we have an effective convolutional neural network for EEG classification, and in this case, our focus is on sleep staging, determining what stage of sleep the person is in, then we have to find out how to validate this. And because we are a medical device company, we want to have FDA clearance to certify that this is safe and effective for medical use. Dr. Liu, let me go back to you and ask you to tell us about the regulatory strategy. How do we go to FDA with our NeuroSom EEG analysis technology, or NEAT software?
You bet. Here, fortunately for us, the strategy is relatively simple in the broader context of machine learning and AI for medical applications. What we've done is we've contacted and engaged the US FDA through a pre-submission process. This process allows us to obtain feedback on what the regulatory strategy for our particular ML approach to sleep scoring. And again, it's pretty straightforward, and we can think of it in three broad domains. The first is the requirement that when we train the model, we have to ensure that whatever the data that goes into the training is representative of the situation when we actually employ the model. So what does that mean? That basically means we have to have the target population, in this case adults, let's just say, and that the data comes from multiple EEG systems. This requirement is essentially the requirement of generalizability. Once you build it and you test it, can it generalize to the population that you're targeting? And so once you train it, then you have to test it. So here the requirement is that whatever you train the machine to do, when you test it, it has to be in a totally different data set. Again, the emphasis there is on generalizability. So we outlined these requirements. And of course, all of this has to be then compared against some outcome. Here we have a two-pronged approach. The first one is the outcome is measured against human raters. So human raters are notoriously unreliable when compared against each other. And so we have to set a gold standard for what a sleep stage is if one were to review the EEG. And so in this, what we do is we have multiple raters, and they rate the EEG. And then we get a consensus agreement from the multiple raters. The agreement then constitutes the ground truth. We take the ML that we constructed, the machine learning method that we constructed, and then we test it against these human raters. In addition, what we have to do is then compare it to some predicate device. And the predicate device in this case is some software that has been cleared by the FDA to also perform sleep staging. Then we apply, we use that predicate to evaluate the same data set that we evaluate our ML. Then we compare the performance of the two software devices. And this is the guidance that the FDA provided to us relative to our strategies, and we think it's pretty straightforward, and we're working on doing that currently.
Very good. So in the validation process, we have what's called a confusion matrix. Here's one from that was used with the ML currently in service. Dr. Liu, could you tell us what a confusion matrix is and how it might be used in the validation process?
You bet. And this follows from my my previous points about the clinical validation or FDA regulatory strategy. So each square here, you'll see on the horizontal axis is the gold standard, and on the vertical axis is the performance of the relevant how should I say, human or our NEAT, or the predicate, in this case, the ENZO software device. And so the gold standard, again, is the consensus agreement of human raters. And we can see how any a single human rater would perform relative to the gold standard, again, the consensus. On the diagonal in the bold orange color, you'll see numbers associated or listed in those squares. And what you'll see are stages of sleep. So we have wake, REM, N1, N2, N3, N3 being deep sleep. And so we know the ground truth, that's the gold standard. And then we can see, for example, how a human would identify a particular segment of EEG and classify it according to these stages of sleep or wake. And you can see that the human is not perfect. That's really the point here. So they're pretty good at identifying wake EEG in the, that's about 95% accurate. Then we can do the same for ENZO. How does ENZO, the predicate, classify these stages? So you can see for wake, it's about 90% accurate. So we can evaluate that for all of the sleep stages. And then we can do that for our technology as well with NEAT. And if you look at wake, we have about 91% accuracy. And so there will be variability. And the question is, how accurate these are, again, relative to each other. And that's how the FDA is going to evaluate it.
So what is the actual criteria? So does the machine learning have to be as good as human raters? Is that the FDA's criteria for this?
No, the FDA criteria for this is actually the predicate. How does the current device, or the device to be considered for clearance, perform relative to a predicate? Is it better? Is it equivalent? Or is it worse?
And the equivalent or the predicate here is the ENZO Sleep,
Yes.
the company that was really one of the first to have an FDA cleared machine learning for EEG.
That's right.
So are we ready to go to FDA submission now?
We're close. We've done most of the validation, the clinical studies here in the FDA nomenclature, and really the task is to pull together the application. So that's what we still have to do.
Excellent. Thanks very much. So I see that Dr. Fernandez-Carranza has joined us. And let me ask you, Mariano, would you be able to give us an overview of the validation of the NEAT software and kind of the current status of that validation as you've seen it?
Basically, for the FDA validation, we have to we had to gather different data sets for the training and testing on one side, and the FDA requires a completely different data set for validation. So this is a short description of the training and testing data set with around 300 subjects. We have 4 data sets, but for this FDA validation, we are going to first validate for only adults, so 22 years old and over. So basically, we're using 2 data sets, 85% of data for training, 50% for testing. This is typical. And then we have a completely different data set, independent, of around 120 subjects, or a little bit more, of all ages. Here you can see the distribution and equal distribution of, or more or less equal distribution of gender, also for 22 plus years old. And we are going to submit a comparison. Here we can see this is called the confusion matrix. This is typical validation for machine learning classification algorithms. So we have the different sleep stages. We want to classify the accuracy and the confidence intervals into brackets. And so we are going to compare against the predicate. Here, this is the performance of our machine learning compared to the predicate, which ours is a little bit better overall. And we are also going to submit a comparison against the human, which we are pretty close to human experts, and even in some categories, need performs a little bit better. So that's basically how the FDA asks for validation. So we are filling out the forms and ready for submission.
Very good. Let me ask just a couple of questions. So the FDA wants us to be as good as the predicate technology, which is from the Enzo Sleep Company that have their device cleared. But don't we also have to be effective in our own right? Don't we also have to show that we're as good as human raters? Or is there any difference in that comparison?
No, I think that for the validation, what they only ask is a comparison against the predicate.
So they're assuming that device is successful and it works well, and so we have to use that as our standard. Yeah, so that's the 510K framework.
That's right.
Yeah.
But well, that's what we discussed during our pre-submission, and the feedback that we got was that it was the predicate. But here, I think it doesn't hurt to provide additional evidence relative to humans, because they will be able to look at the data and make some judgment calls about when the 2 devices doesn't completely agree. But this is my guess. But again, it doesn't hurt to have it, is what I think.
Thanks for joining Neurosom's first webinar on AI technologies in sleep medicine. Our goal is to provide clear explanations of Neurosom's technology development and the validations required for cleared medical devices. Stay tuned for future webinars in this series.